Welcome to NASA Edge. We're at NASA Langley Research Center in the studio with Brian Stevenson from the NASA Goddard Space Flight Center to talk about mixed reality. And we're going to do so today with reference to one of my favorite missions, the magnetospheric multiscale mission. So Brian, my first question for you is, how are we going to do mixed reality as it relates to the very cool, very historically cool and great, wonderful mission that I love so much, MMS?
Well, as you can see, we're in a studio and we've got a very large green screen, and we're going to bring our virtual reality environment here to us. And we're going to bring our users with us. And we're going to go to the clean room at Goddard Space Flight Center, and you're going to be an engineer.
I've always wanted to be an engineer, so that's perfect. Can I be head engineer?
Chief
engineer?
We can do, yeah, chief is good.
Chief engineer, okay, well, chief engineer in the virtual world. But before we go, now this is the clean room, so this is more of an origin story. We're going to go back to the beginning with MMS.
That's correct. We're going to go back where it all began while they were building the satellite right there in the clean room.
I'm ready to go. Can we go?
Let's do it. Let's do it.
Okay, perfect. I'm just going to, I've been told that I look really good in these virtual headsets, so.
So here we are, magically in the MMS clean room.
Oh, this is great. And by the way, it sounds clean. There's like ambient clean noise, clean room noise in here.
Excellent. So I'm going to go ahead and give you a controller.
Okay.
Now you can see me with my controller.
Oh, there you are.
Yeah, I'm waving. So if you need to find me, just look for this.
Yeah, because everything else is kind of mysterious.
If you turn around, you can see the...
oh yeah, there we go.
That's the actual satellite there.
That's the first, I believe.
Yes.
Yeah.
So you're going to help me assemble this.
Okay.
So if you look to your right, there's a table.
As chief engineer, I did know that all this was over here. I was just pretending I didn't know.
So Chief, can you grab me the dual electron spectrometer?
Yes, I would say that's right. Yeah, there you go.
I don't think that's it.
Oh well, it's not. But I knew that. I was just testing you because I'm the chief engineer and I want quality control. You wanted what again? What was it?
The dual electron spectrometer.
That would be
that's
this
right.
one.
Yes,
yeah, there
correct.
you go.
I'm going to go ahead and take that.
It's heavy.
It is kind of heavy. I can feel it.
You want me to
can you grab the dual ion spectrometer for me?
That would be
this
one. Yes.
Exactly.
All right. Yeah.
Right. So we're going to go ahead and put this on the satellite.
All right.
Just slide it right in there.
I think that goes. Yes. There you go.
Perfect. Do you want to put this one on as well?
If you don't mind.
Sure. You're the chief engineer.
That's right. Yeah. Sorry about that. But I'm not one of those harsh taskmaster engineers. I'm kind of a sweetness and light engineer.
I would agree with that.
There you go. All right. So we've oh wait. Let's go ahead and put the other.
Yeah. That's the S band.
Yeah. Sorry. Just a little
Chief engineers need to really get right with their instruments.
I'm hands-on. Yeah, I had to have all the tactile sensations right.
Perfect.
Yes, so there you go. And we have one remaining right here.
Yeah.
Yes, this is the propulsion system.
Yeah.
It's actually not, but
it's a GPS.
Yeah, I was going to say, it looks for my purposes, that looks like a cool propulsion system. Even though it's not, I understand that, just so the world knows. But now, Brian, now you have basically this virtual version of one of the MMS satellites, but this is to scale, right? So an engineer could work on this and have pretty high fidelity in terms of what they could expect when they were really working with the instruments.
Correct. One of the things that we want to do with virtual reality going forward is bring other satellites into clean room environments like this and give the engineers a taste of what it's going to be like to build their spacecraft before they actually get there. So it's very useful.
And I notice there's lots of extra, I shouldn't say extra, that we intentionally designed all that extra space in there. For all the right reasons. You're just going to have to trust me on that. But it really is good to get a visual sense of how everything's laid out.
Yeah, exactly. The engineers can come in here if they can tell how much room they have left. Are they going to add instruments, or how can they maneuver around the spacecraft while they're working on it?
There's only one thing, as far as I'm concerned, that's missing, and I don't know how we're even here, and it's not here, is project scientist Tom Moore, a virtual version. He's like my hero. When I was not studying engineering in college, I always looked up to him and I thought I should study science and engineering, but alas, is he somewhere around here? Because I'd really like him to see my work.
Yeah, I don't know if he's here.
Maybe he's outside on the other side of the garage door.
Well, we can check.
Can we
teleport? Well, I know that it might be a restricted area, but we can check.
Well, the thing is is I'm friends with Tom. So
you're good to go then.
Yeah,
You're good to go. Well,
he gives
no
me
problem.
all kinds of access.
No problem.
So, that's beautiful.
There you go.
That's where I want to go. I want to go out there into space.
Access denied.
Oh.
This is very frustrating as chief engineer. Shouldn't I get a virtual access badge that allows me to do anything I want?
I would agree with that, but
I tell you
said
what.
no.
Let's come out of the virtual space and take a quick break, and we'll let those, Chris and Conrad Schiff, come on, that they can go out in space. I'm going to find Tom Moore and get that virtual access card. So let's take a break, and we'll be back in a second. Man, that's While they're getting ready for the next scene, just a few points of clarification. When you construct or use a virtual clean room like that, how did the scientists respond when they are able to get in there? What kind of things can they do to improve their mission?
Well, I mean, definitely the engineers and the scientists both really, really appreciated it. It gave them a really, a clear view of what was to come. And as we have more missions that come in and we're using more clean rooms and pre-missions, I think we'll find a lot more uses for virtual reality, especially in this way.
Yeah. Perfect. Well, it looks like they're ready on set. So, Chris, take it away.
Hey, thanks, Blair. Conrad, thanks for joining us today.
Hi, Chris. It's good to be here.
Hey, before we actually talk about the MMS mission, Blair's chief engineer for MMS?
Well, chief engineer, I don't know. I mean, the fact that he confused the S-band antenna with the dual electron spectrometer, he needs a little bit of work.
A little bit of work. Now, this is a very cool technology, and this is one of my first times being in this type of setup. As an engineer yourself, could this technology be used in a mission like MMS?
Absolutely. For example, that dual electron spectrometer that Blair was handling so glibly is one of the most sophisticated instruments that's ever been built. And each MMS spacecraft actually has four dual electron spectrometers and 4 dual ion spectrometers around the edges. And in an amazingly quick amount of time, for electrons, 30 milliseconds, it can take a picture of the entire plasma that is around the spacecraft in over 32 energies, which is like 32 different colors on a cell phone.
Now, you've been working on MMS for about 20 years, I understand?
Off and on, yeah, 20 years.
So if you had this technology, let's say 10, 15, 20 years ago, would it be much faster to build a spacecraft like MMS?
Oh, definitely. I mean, back in the day, we had 2D plots. We had to think carefully about how we position things. You would look at whether or not one instrument was looking in the way that it should and versus another instrument. Here you can actually get in there, walk around, see what they're seeing, look where they're looking. You could have a much better idea of whether or not the product you're designing can really be built without any adjustment.
Now, Brian and Blair, when they were in the clean room, there was one spacecraft behind them, but MMS has 4 identical spacecraft. Why do we need 4 for this mission?
Sure. So MMS's primary goal is to look at the interaction between the sun and the Earth. And when we get into the virtual space, we'll see that interaction a little more clearly. But what we're really looking at is something essentially on the lines of space weather. And we can get an idea about how to think why we need 4 spacecraft from regular weather. Suppose you get up in the morning and you want to drive to work, and your commute's, say, 30 minutes. And 20 minutes into your commute, it starts raining. Did you drive into a rainstorm, or did rain suddenly come into the local area in which you live and work? The only way that you can figure out the difference is by calling someone else and comparing. Hey, friend back home, are you seeing it rain there? Because I'm seeing it rain here. Up in space, the 4 spacecraft, by comparing what they see and when they see it, can tell the difference between when a spacecraft flies into something or when something has developed in time.
Now, when you talk about the analogy with the cars, that could be a distance of hundreds of miles, but what are we talking about in terms of the 4 MMS spacecraft?
Sure. So the multi-scale part of MMS is indicates that, in fact, we can adjust the scale between the spacecraft. So the scale isn't fixed pre-launch, and in fact, we've changed it multiple times. What we'll see is between the Earth and the Sun, the field lines tend to bunch up. And on those scales, we tend to have the formation smaller, in the neighborhood of 7 kilometers between them is as close as we've gotten. Out in the tail, where things stretch a bit more, the scale has typically been more on the neighborhood of 40 to 60 kilometers.
Oh, wow, okay. Hey, can we go in and check it out?
Let's take a look.
All right, let's see here.
Let me hold that for you.
Yeah, please, thank you. I don't want to hurt myself. Got to adjust for Blair's head here. Let's see. Tighten that up. Oh, very good.
All right, and then I'm going to hand the probes back to you, so you can do all the driving. I'll just be a disembodied voice.
So right in front of me, I see the Milky Way, which is kind of cool in itself, right there.
But if you turn around, you'll see.
Oh, there you go.
There you go. And so we're looking at the Earth from the outside.
All right.
And the blue lines that you see are a mixture of the field lines, the magnetic field lines that are generated from the Earth.
Okay.
And then the ones a little bit more to the left that look flatter, those are due to the sun.
Okay. Excellent.
And that golden ellipse is the MMS orbit.
Perfect.
Now, if you look to your left a little bit more, you'll see the sun.
Yeah, I can't look at the sun directly, though. You know,
you're in VR. You're okay, Chris.
Okay. Just want to make sure.
Yep. So the sun is the primary source of the solar wind and the magnetic field that's coming in to the front of the Earth's magnetosphere.
So let's just bring it in a little bit closer here. Now, this orbit here, it's really an elliptical orbit.
That's right. But this is the least elliptical of the orbits that MMS has inhabited.
Oh, really? Okay.
In the early part of the mission, this was the orbit designed predominantly for looking at what was on the front side, the day side phenomena, the side between the Earth and the sun. Later on, we've gone to a larger orbit for the second half when we're looking at the tail. And then as we got into extended mission, we've gotten even bigger.
Now, for this extended mission, I understand that you're changing the orientation of the spacecraft?
They have changed from flying in formation to being a string of pearls, which is more stretched out like beads on a string. And then afterwards, they're going to be returned back to formation. But Chris, I got to break it to you. You ran out of quarters.
Now the
no
quarters
more
can't
credits.
Do you have any extra?
No, I'm all out of change.
All right, well, I tell you what, I'll go ahead and stop. Thank you. This is awesome, Conrad. I'm going to come back to Goddard at some point and get back into this
well, you're welcome to come up and visit us anytime you want, and I think would love to have you.
Well, you know, Conrad, now, again, going back to this setup here, as an engineer down the road, this is definitely useful for you.
Absolutely.
Okay.
It's useful for engineers of all sorts, for the science community of all sorts, and I think it's really useful for just even public outreach.
But the cool thing about it is these students who are coming up in high school, middle school, high school, and college, this is going to be second nature to them when they're designing missions in the future.
Yeah, I'm a little jealous, but oh well.
Well, Conrad, thank you so much for coming.
You're welcome, Chris.
We appreciate it. But now coming up, we're going to have an expert on the magnetosphere, Li-Jin Chen, and she's going to be talking with Franklin.
Ready for the next interview. I'm here with Kyle Boyer, who's the virtual reality programming lead for the heliophysics group at Goddard. And Kyle, the big question I have is, you're generating a lot of space, a lot of visuals for scientists. And so tell me a little bit about the responsibility of creating a tool that isn't just visually interesting, but also really represents something that scientists can use.
Certainly, Blair. So the big thing here, virtual reality, it really is a visual representation, but the thing that separates it is it's a visual representation that takes you into the environment you're visualizing. So for the example given earlier with the MMS clean room, you're in a one-to-one scale environment where you can interact with the instruments that you would really be interacting with, in the real clean room. Or for the magnetospheric one, you're actually able to fly around the magnetosphere in real time as opposed to just taking a look at it.
And that's really helpful for the scientists for sure.
Oh, absolutely. When designing this software, most of our interaction is with scientists asking them, what do you guys want in this environment? What would be helpful to you? They give us plenty of feedback, and then it's back to the drawing board for us to develop the things that they want.
And we're going to see a little of that feedback happening right here on the set with Franklin and Li-Jin. So take it away, Franklin.
Thanks a lot, Blair. As Blair said, I'm here with Li-Jin Chen, who is an astrophysicist from the Goddard Space Flight Center. Lee, Jen, how are you today?
Good.
Tell us a little bit about what you do with MMS at Goddard.
Sure. What is the biggest magnet you ever encountered?
Well, I think maybe a magnet that was the size of this controller that could actually fit in my hand.
We are standing on a magnet that is more than 10 million times the size of your hand. Our planet is a giant magnet. This magnet creates layers of shields, protecting us from the blast materials from the sun.
Okay.
Our work with MMS is to look at how these protecting layers work.
Will we be able to see these layers inside of mixed reality?
Certainly. Let's go.
Let's check it out. Oh, Blair had it on extra small. So, okay, we give it a little bit of space there.
Unwinding.
All right, okay. Awesome. Go ahead and tighten it up just a little bit.
Thank you.
Good. Right here are our controllers.
We are near the bow of our Earth spaceship.
Okay.
Here's the bow shock.
Now, a bow shock. What is a bow shock?
Well, like a ship in the water, as it drives in a fast speed, you see a bow wave in front of the ship. This bow shock is the same idea. It forms in front of us as our planet cruises around the sun in the solar wind.
Okay. So what takes place at the bow shock?
The job of the bow shock is to turn the fast and cold solar wind into a warm breeze. MMS discovered something really stunning. At the first contact, the bow shock draws the electron in, make them go faster and faster until the electrons couldn't take it.
Okay.
The streaming breaks down and the streaming energy turns into heat. Past missions have seen the result of this heating. MMS showed us the process itself.
And that is amazing. But after that solar wind passes through the bow shock, it starts to encounter the other layers of the Earth's magnetic field. What happens there?
Very good. Let's come a little bit closer. Just a few Earth radii from the bow shock is this another important protecting layer. It's a transition layer from the Earth's magnetic field, these loopy field lines, and the solar magnetic field. Here, reconnection happens. When it happens, plasma jets is ejected, heating occurs, and the solar magnetic energy is transported to the night side of our magnetosphere.
Now, when you talk about reconnection, magnetic reconnection, that was the primary mission of MMS, right?
That's right. And during this magnetic reconnection happens in the tail, explosive energy is released and precipitated into our magnetosphere, our ionosphere, and creates aurora in the north and south poles. This is during quiet time. When solar storm hit our magnetosphere, aurora goes global to southern latitude, such as Mexico. And intense disturbances get stirred up in the atmosphere, causing disruptions on power grids, GPS, and wireless communications.
So we have a lot of things that take place during magnetic reconnection. We can have disturbances in communications, but then we also get the beauty of Mother Nature in the aurora borealis. Is that correct?
Thanks, nature.
Yes, absolutely. Now, magnetic reconnection, as we said before, is part of the original mission of MMS, but the look at the bow shock that you talked about is something that happened with the extended mission.
Right. So during the extended mission, the orbit of MMS goes through the bow shock all the way into the solar wind. That gives us abundant opportunities to discover new things, new questions, and new answers. We welcome future generations to jump in and explore with us.
And as we were talking about earlier, the data that you are receiving from MMS is data that will be looked at for years and years to come, because you cannot unpackage it all right now to know what is out there.
Still more questions to be answered.
A whole lot more questions to be answered. Lee Jin, I thank you for joining us here today for our mixed reality show. And as Lee Jin continues to fly through space and discover new and exciting things through the magnetosphere, we'd like to thank everybody for joining us here for our show today. For all of our guests from the Goddard Space Flight Center, we thank you for coming. You've been watching NASA Edge.
Buckle up, everyone. That's right on a reconnected field line to the night side of magnetosphere. Woo!
Let's go.